National Electrical Code, or NEC, generally mandates a service disconnecting means for each service entrance. However, Article 230.71 provides an exception for limited loads. Specifically, 230.71 addresses alternating current supply, stating that for services to limited loads as specified in 210.11c, a service disconnecting means is not required where other approved means are provided for disconnecting all ungrounded conductors. This means if the load is limited and there's another approved way to disconnect the power, a dedicated service disconnect isn't always necessary. Think of a lighting circuit that powers only a couple of lights. This qualifies as a limited load. The code requires that the approved means for disconnecting all ungrounded conductors be approved. In such instances, the load center itself, containing a breaker, can serve as the approved means for disconnecting the conductors. Consider a load center with a single 15-amp breaker safeguarding the lighting circuit. This setup might comply with the exception outlined in 230.71, thus not violating the NEC. The key takeaway here is that a dedicated service disconnect might not be mandatory for limited lighting loads if an alternative approved disconnecting means exists, such as a breaker in a load center. In addition to understanding the exception for service disconnecting means, there are several other crucial aspects to consider for a comprehensive and safe electrical installation. Firstly, grounding and bonding form the backbone of electrical safety. Grounding provides a low impedance path for fault current, facilitating the operation of overcurrent protection devices like circuit breakers or fuses. Bonding, on the other hand, ensures that all metallic parts of the electrical system are at the same electrical potential, minimizing the risk of electric shock. The NEC has specific requirements for grounding electrode systems, conductor sizing, and bonding methods, detailed in Article 250, which must be followed meticulously. Secondly, overcurrent protection is essential to prevent damage to equipment and conductors due to excessive current flow. Circuit breakers and fuses are designed to interrupt the current when it exceeds the safe carrying capacity of the conductors. Selecting the appropriate overcurrent protection device involves considering the ampacity of the conductors, the interrupting rating of the device, and any applicable derating factors. Articles 240 and 430 provide detailed guidance on overcurrent protection requirements for various types of circuits and equipment. Thirdly, wiring methods dictate how conductors are installed and protected. The NEC recognizes several wiring methods, including rigid metal conduit, electrical metallic tubing, non-metallic conduit, and cable assemblies. Each wiring method has its own set of installation requirements and limitations. Factors to consider when selecting a wiring method include the environment in which the conductors will be installed, the type of occupancy, and any applicable local codes or regulations. Articles 300 through 398 cover the requirements for different wiring methods. Fourthly, box fill calculations ensure that electrical boxes are not overcrowded with conductors, splices, and devices. Overcrowded boxes can lead to overheating, insulation damage, and potential fire hazards. The NEC specifies the maximum number of conductors, devices, and fittings that can be installed in a box based on its size and volume. Article 314 provides detailed guidance on box fill calculations. Fifthly, conductor ampacity determines the maximum current that a conductor can carry continuously without exceeding its temperature rating. The ampacity of a conductor depends on its size, insulation type, and installation conditions. The NEC provides ampacity tables in Article 310 that list the allowable ampacities for various types of conductors. It is important to select conductors with adequate ampacity to prevent overheating and potential fire hazards. Sixthly, voltage drop occurs when current flows through a conductor, resulting in a decrease in voltage at the load end of the circuit. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Voltage drop can be minimized by using larger conductors or shortening the circuit length. Seventhly, arc fault circuit interrupters, RF size, are designed to protect against arc faults, which are dangerous electrical conditions that can cause fires. ASIs detect the unique current and voltage signatures of arc faults and interrupt the circuit before fire can start. The NEC requires ASIs in many branch circuits that serve dwelling units, particularly in bedrooms and other living areas. Eighthly, ground fault circuit interrupters, or GFCIs, are designed to protect against ground faults, which occur when current leaks to ground. GFCIs detect the leakage current and interrupt the circuit before a person can be injured. The NEC requires GFCIs in many locations where there is a risk of electric shock, such as bathrooms, kitchens, and outdoor areas. Ninthly, surge protection devices, or SPDs, protect electrical equipment from voltage surges which can damage or destroy sensitive electronics. SPD divert excess voltage to ground, preventing it from reaching the equipment. The NEC recommends SPD for all types of electrical systems, particularly those that serve critical loads or sensitive equipment. Tenthly, electrical safety audits and inspections are essential to ensure that electrical systems are installed and maintained in accordance with the NEC and other applicable standards. Audits and inspections can identify potential hazards, code violations, and areas for improvement. Regular audits and inspections can help prevent electrical accidents, reduce the risk of fire, and ensure the safe and reliable operation of electrical systems. Furthermore, accessibility of the disconnecting means is crucial. While the exception in 230.71 might apply, the NEC generally emphasizes that a service disconnecting means should be readily accessible from outside the building. Though the load center is outdoors, its accessibility could still be questioned based on its specific location. It is worth confirming that the meter socket and load center are in good working order and meet all relevant safety regulations. For instance, check for signs of corrosion, damage, or loose connections. It is recommended to consult the local authority having jurisdiction, or OJ, for clarification on any local interpretations or requirements that might apply to your specific installation. Regarding the physical condition of the equipment, inspect the meter socket for any signs of damage such as cracks, corrosion, or loose connections. Ensure that the meter socket is properly mounted and secured to prevent it from being dislodged or damaged. Verify that the meter socket is adequately rated for the anticipated load and that it complies with all applicable safety standards. Similarly, examine the load center for any signs of damage such as rust, corrosion, or water intrusion. Ensure that the load center is properly grounded and bonded to prevent electrical shock hazards. Check the circuit breakers for proper operation and verify that they are correctly sized for the connected loads. Ensure that all wiring connections are tight and secure. Regarding the specific requirements for the service entrance conductors, the NEC provides detailed guidance on conductor sizing, insulation type, and protection methods. The size of the service entrance conductors must be adequate to carry the anticipated load, taking into account any applicable dirting factors. The insulation type must be suitable for the environment in which the conductors will be installed. The conductors must be protected from physical damage by being installed in conduit or other approved raceways. The NEC also specifies the minimum clearances for service entrance conductors from buildings, trees, and other objects. Moreover, grounding electrode system requirements are essential for providing a safe and effective path for fault current to return to the source. The grounding electrode system must consist of one or more grounding electrodes that are connected to the building's electrical system. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. The NEC specifies the minimum size and type of grounding electrodes, as well as the methods for connecting them to the electrical system. Additionally, bonding requirements are critical for ensuring that all metallic parts of the electrical system are at the same electrical potential, minimizing the risk of electric shock. Bonding conductors must be used to connect metallic enclosures, raceways, and equipment to the grounding electrode system. The NEC specifies the minimum size and type of bonding conductors, as well as the methods for connecting them to the electrical system. Furthermore, surge protection is vital for protecting sensitive electronic equipment from voltage surges caused by lightning strikes, power grid switching, and other transient events. Surge protected devices, or SBDs, are designed to divert excess voltage to ground, preventing it from reaching the equipment. The NEC recommends the use of SBD at the service entrance, as well as at individual branch circuits that serve sensitive equipment. Additionally, arc fault circuit interrupters, or FSIs, are essential for protecting against arc faults, which are dangerous electrical conditions that can cause fires. FSIs are designed to detect the unique current and voltage signatures of arc faults and interrupt the circuit before a fire can start. The NEC requires the use of FSIs in many branch circuits that serve dwelling units, particularly in bedrooms and other living areas. In addition to these technical considerations, there are also several administrative and regulatory requirements that must be followed when installing or modifying an electrical system. Firstly, permits and inspections are typically required for electrical work to ensure that it complies with the NEC and other applicable codes and regulations. The permit process involves submitting plans and specifications to the local building department for review and approval. Inspections are conducted by qualified electrical inspectors to verify that the work has been performed in accordance with the approved plans and specifications. Secondly, licensing requirements vary depending on the jurisdiction. In many areas, only licensed electricians are allowed to perform electrical work. Licensing ensures that electricians have the necessary training, experience, and knowledge to perform electrical work safely and competently. Thirdly, documentation is important for maintaining a record of the electrical system. Documentation should include drawings, specifications, permits, inspection reports, and other relevant information. Accurate and up-to-date documentation can be valuable for troubleshooting, maintenance, and future modifications. Fourthly, training and education are essential for staying up to date with the latest codes, standards, and technologies. The electrical industry is constantly evolving, so it is important to participate in ongoing training and education to maintain competency and ensure the safety of electrical systems. It is also important to verify the short-circuit current rating, or SCCR, of the electrical equipment. The SCCR is the maximum amount of fault current that the equipment can safely withstand without sustaining damage or creating a hazard. The NEC requires that the SCCR of the equipment be equal to or greater than the available fault current at the point of installation. To determine the available fault current, a qualified electrical engineer or technician must perform a short-circuit study. The study takes into account the utility source impedance, transformer impedance, conductor impedance, and other factors that can affect the magnitude of the fault current. Once the available fault current has been determined, the SCCR of the equipment must be verified to ensure that it is adequate. If the SCCR of the equipment is less than the available fault current, the equipment must be replaced with equipment that has a higher SCCR, or additional overcurrent protection devices must be installed to limit the fault current. It is also important to consider the ambient temperature when selecting and installing electrical equipment. The ambient temperature is the temperature of the air surrounding the equipment. Electrical equipment is typically rated for a maximum ambient temperature of 40 degrees Celsius or 104 degrees Fahrenheit. If the equipment is installed in an area where the ambient temperature exceeds this limit, the ampacity of the conductors must be derated to compensate for the increased temperature. The NEC provides derating factors for various types of conductors and installation conditions. In addition to derating conductors, it may also be necessary to use equipment that is specifically designed for high ambient temperature applications. This equipment typically has a higher temperature rating and may include features such as forced air cooling or heat sinks. Furthermore, it is important to protect electrical equipment from environmental factors such as moisture, dust, and corrosion. Moisture can cause electrical equipment to short-circuit or corrode, leading to premature failure. Dust can accumulate on electrical equipment, reducing its cooling efficiency and increasing the risk of overheating. Corrosion can damage electrical equipment and weaken its structural integrity. To protect electrical equipment from these environmental factors, it is important to use enclosures that are rated for the specific environment in which the equipment will be installed. Enclosures are available in a variety of materials, such as steel, aluminum, and plastic, and are rated for different levels of protection against moisture, dust, and corrosion. It is also important to perform regular maintenance on electrical equipment to ensure that it is clean, dry, and free from corrosion. This may involve cleaning the equipment with a brush or vacuum cleaner, applying a corrosion inhibitor, or replacing damaged components. In addition to these general considerations, there are also several specific requirements that apply to lighting circuits. The NEC provides detailed guidance on the installation of lighting fixtures, including requirements for mounting, wiring, and grounding. It also specifies the types of lighting fixtures that are permitted in different locations, such as wet locations, damp locations, and hazardous locations. Furthermore, the NEC provides requirements for the control of lighting circuits, including the use of switches, dimmers, and occupancy sensors. Switches must be installed in accessible locations and must be rated for the voltage and current of the circuit. Dimmers must be compatible with the type of lighting fixture being controlled. Occupancy sensors can be used to automatically turn lights on and off based on occupancy, saving energy and reducing operating costs. The NEC also provides requirements for emergency lighting systems. Emergency lighting systems are designed to provide illumination in the event of a power outage. These systems typically include battery-powered lighting fixtures, generators, or uninterruptible power supplies, or UPSs. Emergency lighting systems must be designed to provide adequate illumination for egress routes, such as stairwells, hallways, and exit doors. Finally, it is important to follow all applicable safety procedures when working on electrical systems. This includes wearing appropriate personal protective equipment, or PPE, such as gloves, safety glasses, and arc flash-rated clothing. It also includes de-energizing the circuit before working on it and verifying that it is de-energized with a voltage tester. Never work on live electrical equipment unless it is absolutely necessary, and then only after taking all necessary precautions.